Okay, evaluating determinants by row reduction. So far, we have learned one method for calculating the determinant of any square matrix, and that was cofactor expansion. We learned that you can expand the cofactor along any row or any column, and it will give you a real number. It will associate a real number to that square matrix, which is called a determinant. And we also learned that by experience, we learned that it's not a very computationally easy process to do. It's a recursive algorithm. So for example, if you have a, let's say 4 by 4, and you're expanding the cofactor along the first row, then you will have to calculate 4 cofactors, and each cofactor is going to be -1 to the power of I plus j times the minor, and the minor itself would be a 3 by 3 matrix. So computationally, it's very heavy. There are better ways of calculating the determinant. And today we're going to learn about row reduction technique. First, we take a look at some theorems. Let A be a square matrix. If A has a row of zeros or a column of zeros, then determinant of A is 0. So imagine you have this matrix, and I just put an alpha for a number that could be 0 or something other than 0. If one row or a column of that matrix is 0, then you can expand the cofactor along that row or column, and then it's clear that the determinant is 0, because determinant of A would be 0 times the cofactor corresponding to entry 1, 1, plus 0 times the cofactor corresponding to entry 1, 2, plus 0 times the corresponding cofactor 1, 3, and it's clear that this is going to be 0. Same thing would happen if you have a column of zeros. You can expand the cofactor along that column, and then it's clear that the determinant is going to be 0. The next theorem is the relationship between the determinant of A and the determinant of A transpose. And the theorem says, let A be a square matrix. So A could be any square matrix. Determinant of A and the determinant of A transpose are going to be the same. I'm not going to prove this, but the proof is in the book. But you need to know that when you transpose a matrix, you're not changing the determinant. It has the same determinant. The next thing we're going to look at is, how do row operations affect the determinant? So we know that there are 3 elementary row operations. You can swap rows. You can add a multiple of one row to another row, and you can multiply one row by a non-zero number. So if you're swapping, it's called a swap. If you're multiplying by a scalar, it's called a scale. And if you're adding a multiple of one row to another row, it's called a pivot. And these names actually come from the geometry. If you have the 3 by 3, if you have, for example, a system that's 3 equations, 3 unknowns, then when you add a multiple of one row to another row, then one of the planes starts pivoting, rotating around their line of intersection with the other plane. That's why it's called a pivot. So you remember these 3 row operations. Now we're going to look at how these 3 row operations affect the determinant of a matrix. So let's say we have a matrix A, 1, 2, 3, 4, 5, 6, 7, 8, 9, and you do a row operation on that. You do a row operation like R1 swap with R2, and you get a new matrix 4, 5, 6, 1, 2, 3, 7, 8, 9. You want to know, how would the determinant of A and B be related. So let's begin with part A. That would be a scale operation. If B is obtained from A by multiplying a row or a column by a non-zero scalar k. So for example, if we do, let's say, in order to get B, we are multiplying, let's say, row 2 by 5. And then B would be something like this. 1, 2, 3, and 5 times 4, 20, 5 times 4, 5, 25, 5 times 6, 30, and then 7, 8, 9. If you're doing something like that, if you're doing a scale operation, then the determinant of B is simply going to be 5 times determinant of A. So in this case, determinant of B is going to be 5 times determinant of A. That's what this says. It says that if B is obtained from A by multiplying a row or a column, that's also true for a column, by a non-zero scalar k. So in this example, I chose k to be 5. Then determinant of B is k times determinant of A. And if I'm using this notation, using vertical bars for determinant, I can write it like this. So imagine the first row of A. So what we have here is A. The first row of A has been multiplied by k. Now, determinant of this new matrix is k times the determinant of the old matrix. And when you look at this, it's as if you can factor out the k. You're not factoring out, it's not factoring out. I'm just saying that it's as if you can factor out the k. So, for example, here, if I want to find the determinant of this matrix, and I realize that in the second row, I have 20, 25, 30, and all of them are divisible by 5. That is 5 is a common factor here. I can factor it out. It becomes 1, 2, 3. This divided by 5, 4, by 5, 5, by 5, 6. And then the other two rows do not change. So that would be a valid operation to do. And this new matrix here would be easier to find the determinant for. So it looks as if you're factoring out a common factor from one row or from one column. The same is true for a column. Any questions so far? Okay. Part B is about a swap operation. If B is obtained from A by a row or a column swap, then determinant of B would be negative determinant of A. So the effect of a swap is negation of the determinant. Like in this example here, B is obtained from A by swapping row 1 and row 2. So the new matrix, determinant of the new matrix, is going to be minus determinant of the old matrix. And here you have an example in this notation. This is A, and you can see that the entries are in order from A11 all the way to A33. This is A. And what happens if you swap row 1 and row 2? You get this new matrix, B. And determinant of B would be minus determinant of A. The third row operation that you can perform is a pivot, which is if you're adding a multiple of one row to another row. And the good thing about that is that determinant does not change. So if B is obtained from A by adding a multiple of one row to another row, the same thing is true for a column. If you're doing it by adding a multiple of one column to another column, then the two determinants are going to be the same. So if, for example, A is this matrix here, and you're doing the operation where you're adding k. So if imagine A is this, A11, A12, A13, A21, A22, 23, 31, 32, 33. And you're doing this operation, row 1 plus k times row 2. Then you'll get this matrix here. So k times this has been added to this. So row 1 plus k times row 2 becomes the new row 1. K times this added to this, k times this added to this. This new matrix has the same determinant as matrix A. Are we good? Okay. So a swap will negate the determinant. Multiplying one row or a column by k will cause the determinant of the new matrix will be to be k times the determinant of the old matrix, and a pivot adding one row, adding a multiple of one row to another row, or a multiple of a one column to another column does not change the determinant. So now how can we use these facts in order to find the determinant of this matrix here using row reduction? So I'm trying to figure out the determinant of this matrix. Okay, by looking at these numbers, the first thing that I notice is the second row, there is a common factor of 3. So I can factor it out. One minus 2, 3, 2, 6, 1. Okay, the next thing I can do is I can swap the first row and the second row to have a 1 on top. Notice that it's very similar to the algorithm. It's almost the same thing to the algorithm that we follow when we are doing Gaussian elimination. So we begin with the leftmost non-zero column. We try to bring a 1 on top. And since I have to swap row 1 and row 2, I will negate 1, negative 2, 3. Okay, so, sorry guys, let me just silent this. Okay. So since I am swapping row 1 and row 2, I will negate I will add this negative here. I will multiply by negative 1. So 1, negative 2, 3 becomes the first row, 0, 1, 5 becomes the second row, 2, 6, 1 is the last row, and it stays there. Are you following? Everything is good so far?
Sir, why do you add the negative to the 3?
Because I swapped row 1 and row 2. Swapping has the effect of negating, yes? So if you're swapping row 1 and row 2, for example, then you get this new matrix. That the determinant of the new matrix would be minus the determinant of the old matrix.
Okay, thanks.
So whenever you're swapping, you have to negate. And here, first I factored out the 3, then I had to swap row 1 and row 2, so I multiplied by a negative 1. I'm canceling the effect of that swap. Next, I'm going to try to get a 0 here. And in order to get a 0 here, I would have to do this operation. I would have to do row 3 minus 2 times row 1. And I know this operation does not have any effect on the determinant. So minus 3, 1, negative 2, 3, 0, 1, 5. Negative 2 times this added to this 0, negative 2 times this 4 added to this 10, negative 2 times this negative 6 added to this 5. Sorry, negative 5. Is that clear? 2 times negative 2 times this to this, negative 2 times this to this, negative 2 times this, negative 6 added to this, negative 5. Good. And as I don't need to do anything in terms of the determinant because it doesn't change the determinant. The determinant of this matrix here is going to be the same as the determinant of this matrix here. And the next thing I can do is I can factor out a 10 from this, or a 5 from this. So negative 3. I factor out a 5 from this one. I get 1, negative 2, 3, 0, 1, 5, 0, 2, negative 1. And the last thing I'm going to do is try to get a 0 here. So again, notice that this is the same as the Gaussian elimination algorithm. And for that, I will have to do this operation, row 3 minus 2, row 2, which does not affect the determinant. So 1, negative 2, 3, 0, 1, 5, 0, 0. And if I'm adding negative 2 times this, which is negative 10 to this, I get negative 11. Now, at this point, I have a matrix that is in row echelon form, almost row echelon form. It's a upper triangular matrix. And we learned last class that it's very easy to figure out the determinant of an upper triangular matrix, because if you have an upper triangular or a lower triangular or a diagonal matrix, then in order to get the determinant, you would just need to multiply the elements on the main diagonal. So the answer is going to be negative 15 times the product of these three, which is negative 11. So it's going to be 11 times 15. That's 165. So I'm going to explain that very quickly again. First, I factored out the 3 from the second row. Then I swapped 2 rows, so I had to negate to bring a 1 on top. Then I did this operation, which does not affect the determinant, to get a 0 here. Then I factored out the 5 from the last row. And finally, I tried to get a 0 here by doing this operation, a pivot operation, which does not affect the determinant. And I arrived at this upper triangular matrix for which the determinant is simply the product of the elements on the main diagonal. So I got the answer. Any questions? Okay, so another theorem, if you have a square matrix with 2 proportional rows or columns, then the determinant is 0. So imagine you have A, B, C, D, E, F, and then for the second row, you have K times A, K times B, K times C. I have a situation like that. That is, this row here is K times this row. That's what I mean by proportional rows. Like, for example, you have 1, 2, 3. And here, let's say you have 7, 4, 9. But for the second row, you have a multiple of first row. For example, 5 times this 5, 5 times this 10, 5 times this 15. In that case, the determinant of this matrix is going to be 0. So if A is a square matrix with 2 proportional rows or 2 proportional columns, the determinant is going to be 0. And the reason for that is you can do this row operation. So determinant of this matrix, 1, 2, 3, 5, 10, 15, 7, 4, 9, is going to be the determinant of this matrix if I do row 2 minus 5 row 1. I get 1, 2, 3, 7, 4, 9. but here I get 0, 0, 0. And we just learned that if you have a matrix with a row or column of all zeros, then the determinant is going to be 0. So this is going to be 0. And sometimes you can just look at that and by inspection tell that the determinant is 0. So for example, when you look at this one, you may notice that row 2 is 2 times row 1. 2 times 1, 2, 2 times 3, 6, 2 times negative 2, negative 4, 2 times 4, 8. So here we have two proportional rows. It doesn't have to be the first and second. It could be any two proportional rows. It could be, for example, row 1 and row 4. As long as they're proportional, it's very easy to prove that the determinant is 0. Any questions? Okay. Next example, using column operations to evaluate determinant. Okay, so this is an example to show you that sometimes it's easier to do column operations rather than to do row operations. So sometimes it's a smart choice to do column operations. So let me try to explain that. 2706 0630 731 minus 5. So when you look at this matrix here, it's going to be a lot of work trying to make this matrix upper triangular. However, it would be very easy to make this lower triangular because here almost all of them are zeros except for 3 and 6. And we really don't care whether it's upper triangular or lower triangular. As long as it's triangular, it's very easy to get the determinant. You just multiply the elements and the main diagonal. And notice that if I just do a simple column operation, if I do column 4 minus 3 times column 1. And also notice that this type of row operation, column operation, that is multiplying, adding a multiple of one column to another column, does not affect the determinant. So this determinant is going to be the same as determinant of this matrix. 1, 2, 0, 7, 0, 7, 6, 3, 0, 0, 3, 1. And then negative 3 times this added to this, negative 3 times this added to 6, 0. No change here. And negative 3 times this is negative 21. Negative 21 added to 5 is negative 26. Negative 3 times this 21, negative 21 added to 5, negative 26. Okay. And just by doing one column operation, we made this lower triangular. That is, all the entries here are now zeros. So the determinant is going to be 1 times, 7 times, 3 times, minus 26. So whatever that is. Are we good? So you have to look out for that. Sometimes it's easier to do just a column operation or a couple of column operations. That would be faster. And the other thing I want to emphasize is that you can also use a combination of both methods, the cofactor expansion method and the row reduction method. Sometimes it makes sense to do a combination. So I'm going to do this example for you, example combining the two methods, showing you how you can do that. 3, 5, minus 2, 6, 1, 2, minus 1, 1, 2, 4, 1, 5, 3, 7, 5, 3. So since there are no zeros, it would be very difficult to do by cofactor expansion. You will have to expand the cofactor along a row or a column, and then for that you will have to calculate 4 minors, and each minor would be the determinant of a 3 by 3 matrix. That can take very long. Now, what if you try to do row reduction? If you do the row reduction all the way, you will also get the answer by reducing this to a matrix that's upper triangular. That would also make sense. But now I'm going to do a combination of both. So first, I would try to get a 0 here, a 0 here, and a 0 here by doing pivot operations. So I will have to do row 1 minus 3 row 2, row 3 minus 2 row 2, and row 4 minus 3 row 2. Actually, I'm using this 1 here to introduce zeros above it and below it. So the second row does not change, but all the other rows will change. Negative 3 times this to this 0, negative 3 times this negative 6 added to this negative 1, negative 3 times this positive 3 added to this 1, negative 3 times this negative 3 added to this 3. Negative 2 times this to this 0, negative 2 times this negative 4 added to this 0, negative 2 times this 2 added to this 3, negative 2 times this negative 2 added to this 3, negative 3 times this to this 0, negative 3 times this negative 6 added to this 1, negative 3 times this positive 3 added to this 8, and negative 3 times this negative 3 added to this 0. Okay, so now you can see at this point I have a matrix, and notice that these two have the same determinant, because these operations, none of them change the determinant. But now we have a matrix that we can easily find the determinant for by cofactor expansion. We just need to expand the cofactor along the first column. Because this is 0, this is 0, this is 0, we will have to just calculate the cofactor corresponding to the second position. So the cofactor expansion of this is going to be 0 times cofactor 1, 1, plus 1 times the cofactor 2, 1, plus 0 times cofactor 3, 1, plus 0 times cofactor 4, 1. And you see all of these are going to be 0. They don't matter. So I just need to figure out what this cofactor is. And this cofactor is going to be minus 1 to the power of 2 plus 1 times the corresponding minor. So it's going to be minus, notice that 2 plus 1 is 3, and negative 1 to the power of 3 is minus 1. Now, if I get rid of this row and this column, I get the minor minus 1, 1, 3, 0, 3, 3, 1, 8, 0. And to make things even more exciting, I'm going to use the arrow technique to calculate that. Is it clear so far? So this is C11. Any questions? Okay then. So let's use the arrow technique for this last one. 1, 0, 1, 1, 3, 8, 3, 3, 0. And then I have to repeat these two columns, the first two columns. And then the product of these is going to be 0, plus the product of these, that's going to be 3, plus the product of these, 24, minus, open brace, product of these, 0, product of these, minus 24, and product of these, 9. So that's going to be 27, then negative 24 plus 9 minus 15 minus 15, that's plus 15. So 27 plus 15 is going to be 42. However, the final answer is going to be minus whatever this is. So the determinant of the matrix, if it's A, would be minus the minor 2, 1, which is going to be minus 42. Okay, yes, question? Nicola?
Yeah, sir. Shouldn't the plus 24 be 0?
Okay. Oh, you are right. You are right. I made a mistake here. There is a 0 here. So you have negative, so you have 0, then you have positive 3. No, this is gone. You're right. That's not correct. That's 0. And then other way, you get 0, minus 24, and positive 9. Okay, so that makes everything different. So this one is going to be 3 plus 15, which is 18. So 24 minus 24 plus 9. Yeah, so it's 3 minus 15, 3 plus 15, that's 18. So the answer is minus 18. Thanks for mentioning that. I'm going to, so far we got minus 18 using a combination of all the techniques that we have learned so far. Row reduction, then we did cofactor expansion, and then we used the arrow technique. I would like to make sure that this is the right answer by continuing row reduction from this matrix here. So let's see whether we get negative 18. So in order to get the matrix to become a matrix that is upper triangular, I can swap the row 1 and row 2, and for that I have to multiply by negative 1. At the same time, I want to swap row 3 and row 4. So this row here and this row here, I also swap. Yes, so I'm doing 2 row operations. Row 1 swap with row 2 to get a 1 on top, and row 3 swap with row 4. That means I have to multiply by negative 1 twice. Then I'll get this. 1, 2, negative 1, 1. 0, negative 1, 1, 3. 0, 1, 8, 0. And then 0, 0, 3, 3. So actually you can see that these two cancel out. It's like a 1. Next, I have to do a pivot in order to get a 0 here. So I would do row 3 plus row 2. That gives me 1, 2, negative 1, 1. 0, negative 1, 1, 3. 0, 0, 9, 3. 0, 0, 3, 3. And then I would try to get a, I can try to get a 0 here, or I can factor out 3 from this, factor out 3 from that one. Then I'll have to deal with the smaller numbers. let's just swap these two rows. And because I swapped, I had to negate. And finally, I can get a 0 here by doing row 4 minus 3 row 3, which does not change the determinant. 1, 2, 1, 0, negative 1, 1, 3, 0, 0, 3, 3, 0, 0. Negative 3 times this to this is 0. Negative 3 times this is negative 9 added to this negative 6. At this point, I can see that I can just multiply the entries on the main diagonal, and I would get
Wait, sir.
I would get 18. So the
Sir.
answer is minus 18. Yes.
Why isn't the like in the second to last matrix, why isn't the last entry 9?
This entry, why is it 9?
No, the one next to it on the right.
I swapped these two.
Oh, wait, never mind. Sorry.
Yeah, the reason I swapped them was that I wanted the 3 here. So I swapped them, and because of that swapping, I got this negative here. And the next row operation was a pivot, which does not change the determinant, but will give me a 0 at this position. So now you can see that 1 times negative 1, 3 times negative 6, that would be 18. You have a negative here, so negative 18, we get the same answer. So first, I used the combination of all the methods, and next, I used row reduction all the way. You always get the same answer because there is only one determinant.
Sir?
Yes?
Could you factor out the 3 on the last two rows or no?
Exactly, you could do that as well. So at this point, you had the option of factoring out a 3 from this row, and then factoring out a 3 from this one. You would have a 9 outside. Yes, but still you'll get the same answer.
Okay.
So let's just take a look at one of the exercises that we did from 2.1. Where you had to find the determinant. Yeah, and so for this one, it's easy because it's already in triangular form. Yeah, like this one. Yes. So this matrix would be difficult to do just by the method of cofactor expansion. However, by the row reduction, it would be much easier to do. I'm going to give you some time to work on this, and then I'll do it on the board. Okay. So this is the matrix that we're trying to figure out the determinant for using a row reduction or a combination. You can use a combination of row reduction and cofactor expansion. It's a good idea to always start with a row reduction. So I'm going to give you a hint how to start it. So I would do it like this. I would try to get a 0 here, here, and here in the first column. So my first step would be to do a few pivot row reductions. That is row 2 minus 4 row 1, row 3 minus 5 row 1, row 4 minus row 1. And then from there on, I can do a cofactor expansion, or I can keep doing row reduction. So I'm going to give you some time, 5 minutes, work on this, and then I'll do it on the board. Okay, let's do this one using beginning by row reduction. I'm going to do row 2 minus 4, row 1, row 3 minus 5, row 1, and row 4 minus row 1. And this will not change the determinant. None of them will change the determinant. All of them are pivot operations. Negative 4 times this added to 0. Negative 4 times this negative 20, negative 21. Negative 4 times this positive 8 added to this 13. And negative 4 times this negative 20 added to this negative 25. So if I make a mistake, let me know. Negative 5 times this added to this 0. Negative 5 times this negative 25 added to this negative 27. Negative 5 times this positive 10 added to this 14. And negative 5 times this negative 25, negative 29. And then this minus this 0, 5 minus 5, 0. Negative 3 minus so negative 1 times this minus 1 here, and negative 1 times this negative 5 added to this negative 2. Okay, so now we have a matrix with a column that is almost every entry is 0 except for the first one. So this is going to be 1. So negative 1 to the power of 1 plus 1, because that's the position here. That's position 1, 1. Times the corresponding minor, which is going to be negative 21, 13, negative 25, negative 27, 14, negative 29, 0, negative 1, negative 2. So I could also continue doing row reduction, but I believe maybe it's easier at this point to just use cofactor expansion along the first column. So just want to make sure that I did not write anything incorrectly. Okay, so in order to find this determinant, I can use another cofactor expansion. So if you remember that sign matrix, plus, minus, plus, minus, plus, minus, plus, minus, plus. So this determinant here is going to be, here we have a minus, and here we have a plus, and here we have a 0. So the cofactor expansion along the last row is going to be 0 times the corresponding cofactor plus negative 1 times the corresponding cofactor plus negative 2 times the corresponding cofactor. But you can see that at this position, the cofactor is going to be minus the minor. At this position, the cofactor is going to be the same as the minor. So I have negative 1 times negative 1. So this second negative 1 comes from this negative over here. The corresponding minor is going to be minus 21, minus 25, minus 27, minus 29, plus minus 2 times the corresponding cofactor, corresponding minor, which is going to be this. So we get, what do we get? Plus minus 2 times, okay, use my calculator for this. I have 21 times 29 minus, open brace, 25 times 27, close the brace, equals minus 66. Negative 2 times for this one, I have 21 minus 21 times 14 minus, open brace, negative 27 times 13, close the brace, 57. 57 times minus 2 minus 66. I got minus 180. You also got minus 180? Let's try this.
Yeah.
That's okay. Good.
Sir,
Yes.
what does it say next to the -6 there?
Oh, it's a minus 66.
Okay, thank you.
That actually comes from here. This is just 1, so I didn't write it. So this times this minus this times this, that gave me the minus 66. Okay,
Sir.
very good. I'm done with my lecture. I also opened the next section, 2.2.